Our universe is filled with objects that break the rules of physics. We are about to explore 25 deep space anomalies that challenge everything we know about matter. By the end, you will understand how these cosmic puzzles could completely rewrite our understanding of reality. Why do galaxies spin too fast without flying apart? And what causes bursts of energy so powerful they outshine entire galaxies in a millisecond? What do you believe is the universe's greatest unanswered question? A galaxy spins with such ferocious speed that its stars should be flung into the void, yet they cling together as if held by an invisible hand. This is the first great cosmic contradiction that forced us to acknowledge dark matter. For decades, the rotation curves of galaxies baffled astronomers. The outer stars were moving far too quickly for the gravitational pull of the visible matter alone. Something unseen, something immense, was providing the extra gravity to keep these galaxies from flying apart. The pioneering work of Vera Rubin provided the undeniable evidence, showing this wasn't a fluke but a universal feature of spiral galaxies. We now call this the dark matter halo, a vast, ghostly sphere that cradles every galaxy. It does not emit, absorb, or reflect light, making it completely transparent to every telescope we have. It interacts with our familiar world only through gravity. Think of it as the universe's greatest phantom, a presence we can only feel by its pull on everything we can see. The nature of this substance is perhaps our biggest puzzle. It appears to be made of particles that are not the protons, neutrons, and electrons that build our world. These are non-baryonic particles, entirely alien to the standard model of particle physics. The Bullet cluster offers stunning proof. When two clusters of galaxies collided, the hot gas of normal matter, which we can see with X-ray telescopes, slammed together and slowed down. But the dark matter, inferred by its gravitational lensing effect, sailed right through the collision completely unaffected. It literally became separated from the visible universe. This tells us dark matter doesn't even interact with itself in the normal way. If most of the matter in the cosmos is this invisible, unknown substance, then what are the building blocks of reality truly made of? This fundamental question of what holds galaxies together inevitably leads us to another, where the force of gravity itself seems to behave in ways we cannot explain. The same invisible hand that grips individual galaxies also orchestrates the motion of entire galactic cities. We observe immense clusters, each containing thousands of galaxies, moving with a collective velocity that defies logic. The sheer amount of visible matter in these clusters is simply not enough to generate the gravity required for such rapid, coordinated motion. This is a gravitational anomaly on a truly colossal scale, where the ghostly presence of dark matter must be acting as the primary cosmic architect, binding these metropolises together. Yet, even when we account for dark matter, the story grows more complex. Data from powerful instruments like the Planck satellite reveal peculiar motions that strain our leading model of the universe. The clusters seem to be flowing in ways that are inconsistent with the grand cosmic blueprint. Experts like Dr. Netta Bokhal, who dedicated her career to mapping these large-scale structures, found hints of a deeper puzzle. The light from distant objects is warped by the cluster's gravity in unexpected ways, a phenomenon known as gravitational lensing that suggests there is more mass or a different kind of influence than our models predict. Even the superheated gas that glows between the galaxies within a cluster, its temperature and distribution, points to sources of energy or physical processes we have not yet accounted for. This leads to another layer of mystery, the missing baryon problem. we can calculate how much ordinary, visible matter, the baryonic matter made of protons and neutrons, should exist in the universe. But when we look at these vast clusters, a significant portion of that predicted ordinary matter is simply not there. It is not dark matter, it is the familiar stuff of stars and planets that has seemingly vanished from sight. Perhaps it exists in a diffuse, hard-to-detect form, like a web of incredibly hot gas stretching between galaxies. Furthermore, the cosmos may not be as evenly mixed as we once thought. The discovery of immense cosmic voids, like the KBC void, a region of space hundreds of millions of light-years across that is strangely empty of galaxies, challenges our assumption of universal homogeneity. When we zoom in on a specific cluster, like the famous Coma cluster, the anomalies become even more pronounced. Its strange X-ray emissions hint at powerful, unaccounted energy sources stirring within its heart. So what does this erratic, unexplained motion tell us? It suggests that the forces shaping the largest structures in our cosmos are not yet fully written in our textbooks. Just as we grapple with these immense gravitational puzzles, we are drawn toward an even stranger phenomenon, one where the fabric of space and time itself appears to warp in ways we cannot predict. In the quiet darkness between galaxies, a sudden flash of radio energy erupts with the power of 500 million suns, all in less than the blink of an eye. This is the baffling reality of fast radio bursts, signals so immense they momentarily outshine their entire home galaxies, only to vanish without a trace. Their discovery in 2007 by astronomer Duncan Lorimer, while reviewing old data from the Parkes radio telescope, opened a door to one of the most urgent mysteries in modern astrophysics. The central question is deceptively simple: what natural process can possibly concentrate such staggering energy and release it so abruptly? The leading suspects are exotic objects like highly magnetized neutron stars, known as magnetars, which could produce colossal stellar quakes, or perhaps intricate dances between black holes and their accretion disks. Yet the sheer power involved strains even these dramatic explanations. What makes these signals even more valuable as cosmic tools is their journey. As a burst travels across the universe, it smears out, with lower frequency radio waves arriving slightly later than the higher ones. This dispersion measure acts like a cosmic odometer, telling scientists how much ionized material, the diffuse gas between galaxies, the signal has traveled through. For years, models predicted a certain amount of this ordinary baryonic matter should exist in the cosmic web, but it remained missing from our observations. Fast radio bursts have now confirmed its whereabouts, effectively weighing the invisible strands of the universe. The plot thickened with the discovery of repeaters. While most bursts are one-off cataclysmic events, one source, designated FRB 121102, has fired off multiple times from the same distant dwarf galaxy. This repetition rules out any source that destroys itself in the process, like a single stellar explosion. The Canadian HIME telescope, with its unique ability to scan huge swaths of sky, has since catalogued hundreds of these bursts, revealing yet more repeaters and even suggesting strange periodic patterns in their activity. Why do some sources erupt again and again while others fall permanently silent? Each new detection deepens the puzzle, challenging our fundamental understanding of high-energy physics. This profound imbalance in the behavior of cosmic energy finds a strange parallel in the very substance of reality, where a fundamental symmetry of the universe was broken at its birth. If the universe were perfectly fair, nothing would exist at all. In its first moments, the cosmos should have created equal amounts of matter and antimatter, partners that annihilate each other upon contact in a flash of pure energy. The entire cosmic story should have ended almost as soon as it began, leaving behind a vast, empty sea of light. Yet here we are in a reality built almost entirely from matter. This profound asymmetry is one of the most fundamental puzzles in all of physics. Why does any solid substance remain? The Big Bang theory predicts a balanced creation, but our observations reveal a universe overwhelmingly dominated by one type of particle. We have searched the skies for regions dominated by antimatter, entire antimatter galaxies or stars, and found none. Experiments like the Alpha Magnetic Spectrometer, mounted on the International Space Station, have detected antimatter particles like positrons, the antimatter twins of electrons, but only in tiny numbers that are consistent with secondary cosmic processes, not a primordial abundance. The evidence points to a clear conclusion. For every billion annihilations that occurred in the early universe, one single particle of matter survived. That 1 in a billion asymmetry is the reason you and everything you see exists. The great physicist Andrei Sakharov outlined the 3 necessary conditions for this to happen, a process called baryogenesis. One key ingredient is a violation of something known as CP symmetry. This is a subtle but profound concept. It suggests that the laws of physics treat particles and their mirror image antiparticles slightly differently. Imagine a fundamental reaction that proceeds one way for matter, but when you swap matter for antimatter and view it in a mirror, it proceeds at a slightly different rate. That tiny difference over the immense scale of the newborn cosmos could have tipped the scales. Experiments at facilities like CERN are hunting for these minute violations in the behavior of particles like neutrinos and their antineutrino counterparts. They are looking for any crack in the perfect symmetry, any small preference that nature might have for matter over antimatter. So far, the CP violation we have observed is not nearly enough to account for the overwhelming matter dominance we see. This means there must be new physics, new particles or forces beyond our current models that played a decisive role in those first critical moments. The question of why there is something rather than nothing is not just philosophical, it is a physical anomaly written into the fabric of every atom. This mysterious absence of antimatter in the vast cosmic landscape finds a strange echo in the discovery of even greater absences, enormous regions of space where even ordinary matter seems to have gone missing. These vast, silent deserts of space stretch for hundreds of millions of light years, containing almost nothing at all. The Boötes void is one such emptiness, a spherical region so barren that if our Milky Way were at its center, we would have seen no other galaxies until the 1960s. The existence of these great cosmic voids defies our expectations for how the universe should be structured. According to our best models, gravity should have pulled matter into a more evenly distributed cosmic web, not carved out these staggering vacancies. Their sheer size and emptiness suggest that another force, perhaps dark energy, is actively pushing space apart within these regions, counteracting the pull of gravity. Cosmologists like Laura Mersini-Horton study these voids as windows into the vacuum energy of space itself, probing the quantum fluctuations from the universe's birth that may have been amplified into these vast nothingnesses. One of the most telling clues comes from the galaxies that huddle at the very edges of these voids. Their movements are peculiar, as if they are flowing away from the emptiness, pushed by some repulsive influence. This strange motion challenges the very laws of gravity as we know them, suggesting that either our understanding of gravity is incomplete on the largest scales, or that the voids themselves exert a kind of negative gravitational pull. We can even see the ghostly imprint of these voids on the oldest light in the universe, the cosmic microwave background. This is known as the integrated Sachs-Wolf effect. As light from the Big Bang's afterglow travels through a cosmic void, it must climb out of a gravitational well that has become shallower due to the accelerating expansion of the universe. The light gains a tiny amount of energy, making the background microwave radiation appear slightly warmer in that direction. The opposite is also true for dense clusters of galaxies. A stunning example is the Eridanus supervoid, an immense cold spot in the cosmic microwave background that correlates with a vast underdense region. This cold spot is a profound anomaly, a potential signature of a primordial defect in the fabric of spacetime or a rare fluctuation from the very first moments of creation. Why do these immense voids exist, and what do they tell us about the true nature of gravity and cosmic evolution? They are the universe's grandest empty stages, and their profound silence speaks volumes about the forces we have yet to understand. This exploration of immense cosmic emptiness now draws our attention to the opposite extreme, where the universe hurls unimaginably energetic particles across intergalactic space. A single subatomic particle carrying more energy than a professionally thrown fastball can arrive from the depths of space. This is the staggering reality of ultra-high energy cosmic rays, atomic nuclei traveling at nearly the speed of light with energies millions of times beyond what our most powerful particle colliders can achieve. Their existence is a profound cosmic anomaly, a direct challenge to our understanding of physics. The central puzzle is not just their incredible power, but their very journey to us. The space between galaxies is threaded with magnetic fields, which should act like a cosmic maze, scattering and redirecting these charged particles until their original paths are completely lost. Yet, against all odds, some of them reach our planet with trajectories that point back to their extragalactic origins. Pioneering researchers like Pierre Auger, whose name now graces massive observatories designed to catch these rare events, helped confirm that these are not local phenomena. They are intergalactic messengers, but messengers from sources we cannot identify. The mystery deepens with a theoretical barrier known as the GZK cutoff. This is a fundamental limit imposed by the universe itself. A proton with energy above this threshold should not be able to travel vast cosmic distances. As it flies, it would inevitably collide with the faint photons of the cosmic microwave background, the leftover glow from the Big Bang. In these collisions, the proton would lose energy, rapidly decaying below the cutoff long before it could ever reach our detectors. The fact that we observe particles with energies far beyond this limit means one of two things. Either these particles did not travel very far, which contradicts their extragalactic origin, or our understanding of high-energy particle physics is fundamentally incomplete. When we chart the number of cosmic rays against their energy, we see a distinct curve with a feature astronomers call the ankle, a bend in the spectrum that marks the transition from galactic to extragalactic cosmic rays. This tells us we are dealing with at least two different populations of accelerators, yet we struggle to identify either. Projects like the Telescope Array, a vast field of detectors in Utah, have recorded legendary events. One was dubbed the "Oh my God" particle, a single proton with so much kinetic energy it was compared to a bowling ball dropped on your foot. Its detection was so statistically improbable it seemed to defy the laws of physics. What natural engine could possibly accelerate a mere atomic nucleus to such an extreme? Suspects include the violent environments around supermassive black holes in active galactic nuclei, or perhaps the cataclysmic mergers of neutron stars. Yet when we look back along the incoming paths of these ultra-high energy events, we find no obvious, powerful source in that particular patch of sky. They appear to come from nowhere or everywhere. Why are these cosmic accelerators so effective and yet so perfectly hidden? This search for the universe's most powerful particle accelerators naturally directs our gaze towards the dense, spinning remnants of dead stars where matter is compressed into states so bizarre they defy imagination. Deep within the heart of a city-sized star, a cosmic clock suddenly skips a beat. This is the strange reality of pulsar glitches, where a neutron star, the compressed core of a dead sun, can change its spin in a fraction of a second for no reason we can see. These objects are nature's most precise timekeepers, their lighthouse-like radio beams sweeping past us with metronomic regularity. Then, without warning, a glitch occurs. The star might speed up by a tiny but significant amount. A stellar stumble that releases more energy than our sun will emit in 100,000 years. For decades, astronomers like Andrew Lyne have meticulously tracked these events, finding patterns that defy our best models of stellar interiors. The leading explanation points to the star's mysterious inner layers. A neutron star is thought to have a rigid crust of iron nuclei, floating atop a core of superfluid neutrons, a substance with zero viscosity that can flow without any friction. Think of it as a spinning magnet encasing a quantum ocean. In this model, the superfluid rotates by forming tiny whirlpools called vortices. Normally, these vortices are pinned to the solid crust, keeping the two components locked together. But as the star gradually slows down over millennia, a tension builds. The superfluid wants to keep spinning fast while the crust slows. Suddenly, millions of these vortices unpin all at once, transferring a massive amount of angular momentum to the crust and causing the observed speed up. This sounds elegant, but the reality is far messier. The Vela pulsar is a famous offender, experiencing regular glitches that should, in theory, help us calibrate our models. Instead, its behavior is wildly unpredictable. The size and timing of its glitches do not follow a clean pattern, and sometimes the star's rotation recovers in ways that suggest something far more complex is happening deep within. Some events might be triggered by starquakes, where the incredibly dense crust fractures and shifts, suddenly changing the star's moment of inertia. Others could involve dramatic reconfigurations of the star's immensely powerful magnetic field, which is trillions of times stronger than Earth's. These internal shifts could be stirring the superfluid core, triggering the sudden release of energy. The fundamental question remains, how does such a small object store and manage such immense rotational energy? And what does its erratic behavior reveal about the nature of matter under the most extreme conditions imaginable? These tiny, glitching stars are laboratories for quantum physics on a cosmic scale, offering us a glimpse into a world where the rules of fluid dynamics are rewritten. As we ponder the turbulent quantum oceans within these stars, our search for cosmic structure leads us to gaze upon the largest and most serene objects in the universe. A silent architecture spans the cosmos, a ghostly scaffolding connecting every galaxy in a vast dark web. These are the cosmic filaments, immense threads of dark matter and diffuse gas that trace the largest structures in the universe. We have never seen one directly, for they are so tenuous they are effectively invisible. Our knowledge of them comes from the painstaking work of mapping the positions of millions of galaxies, revealing that they do not drift randomly but are strung along these invisible lines like pearls on a string. Pioneering cosmologists like J. Richard Gott III used such maps to reveal the skeleton of the cosmos, a web far grander than anyone had imagined. The sheer gravitational pull of these filaments dictates the motion of entire galaxy clusters, funneling them along dark highways toward dense nodes. Yet when we calculate the mass required to wield such gravitational influence, we find a familiar puzzle. The filaments contain far more mass than the visible galaxies within them can account for. This points again to the dominant, invisible hand of dark matter, whose tendrils form the primary framework of this cosmic web. But another, more subtle mystery is woven into these threads, the case of the missing baryons. We know how much ordinary matter, the protons and neutrons that make up stars and planets, should exist in the universe. For decades, a significant portion of it was unaccounted for. The leading theory was that this missing ordinary matter was hiding in the filaments, in the form of a superheated, incredibly diffuse gas known as the warm-hot intergalactic medium, or WIM. This gas is so hot it emits only faint X-rays and so spread out that its density is barely more than a vacuum. How do you find something that is practically nothing? The answer came from looking at the light of incredibly bright, distant objects called quasars. As the light from a quasar travels through a filament on its way to Earth, the gas in the WIM absorbs specific wavelengths, leaving extremely faint fingerprints called absorption lines in the quasar's spectrum. It is like detecting a thin fog by the specific colors it removes from a distant lighthouse beam. This is how we confirmed that the missing baryons were indeed there, woven into the cosmic web all along. Yet even this discovery holds anomalies. Take the Sculptor Wall, a colossal filament complex near our own galactic neighborhood. Studies of the galaxies within it show peculiar velocity flows, movements that cannot be fully explained by the gravitational pull of the visible matter and the modeled dark matter. It is as if an additional, unseen force is gently tugging at them, suggesting that our maps of the cosmic web and our understanding of the matter within it are still incomplete. These filaments are not passive strings, they are dynamic rivers of influence that govern where and how galaxies form and evolve. How does this faint, hot gas cool and condense to fuel the birth of new stars? What other secrets are hidden within the universe's transparent skeleton? The very light we use to probe this invisible web can itself behave in ways that defy our expectations, revealing even deeper layers of cosmic mystery. A star located over 1,000 light-years away flickers in a pattern unlike anything in our cosmic records. This is Tabby's star, a celestial object whose bizarre dimming episodes have ignited one of the most public and perplexing detective stories in modern astronomy. The Kepler Space Telescope first spotted its strange signature, capturing light curves with deep, irregular dips. At times, the star's brightness would plummet by over 20%, a staggering amount that rules out a simple orbiting planet. A planet would cause a small, regular, and symmetrical dimming. What we see instead is a chaotic, lopsided pattern of shadows, as if something with a complex, jagged shape were drifting in front of the star. The astronomer who led its initial study, Tabby, proposed a range of natural explanations. Perhaps a vast, fragmented swarm of comets was circling the star, or a cloud of fine interstellar dust was filtering its light. Yet each hypothesis faced a challenge. A comet swarm would likely produce detectable infrared radiation from the warmth of the debris, which we do not see in sufficient amounts. The dust explanation struggles to account for the sheer depth and asymmetry of the dimming events. The mystery deepened with the discovery of a long-term trend. Over the course of the Kepler mission, the star's overall brightness also appeared to be gradually fading. This combination of sudden, dramatic dips and a slow, secular dimming is exceptionally rare and difficult to reconcile with any single known stellar phenomenon. Could the star itself be behaving strangely from within? Some scientists point to intrinsic variability, suggesting the star might be recovering from a past cataclysm, like a collision that absorbed a planet, leaving behind a swirling disk of residual material that occasionally blocks our view. Others wonder if we are witnessing a new, unclassified phase of stellar evolution. While the idea of alien megastructures, vast energy-collecting constructs, captured the public imagination, the scientific community continues to search for a natural cosmic mechanism that can explain all the data. The core anomaly lies in the light curve itself, a graph that tells a story we cannot yet read. Why is the dimming so deep, so irregular, and so asymmetric? What object or process in nature creates such a jagged, unpredictable shadow? Tabby's star forces us to question the completeness of our stellar models and reminds us that sometimes the most profound discoveries begin with a single, flickering point of light that refuses to follow the rules. This search for hidden structures blocking starlight finds a parallel in a far more violent and invisible cosmic phenomenon, where the very fabric of space-time is set ringing. A subtle tremor in space-time, detected by our most sensitive instruments, leaves no trace in the light of our telescopes. This is the unsettling mystery of unidentified gravitational wave signals. When the LIGO and Virgo observatories first sensed these ripples in the fabric of the cosmos, they opened a new window onto the universe's most violent events. But not every signal fits the expected pattern of colliding black holes or merging neutron stars. Some events arrive with a strange statistical signature, a whisper from the darkness that does not match any known cataclysm. The legendary physicist Kip Thorne, one of the architects of this new field of astronomy, has long speculated that the gravitational wave spectrum could reveal phenomena far beyond our current catalog, from the vibrations of cosmic strings to the echoes of phase transitions in the universe's fiery infancy. These would be tremors from the very birth of space-time, a fundamental reshaping of reality that left a permanent imprint on the cosmos. The anomaly known as GW 1921 stands as a prime example. It was a collision, but the objects involved were perplexing. Both were of a mass that should not exist, falling squarely into the theoretical mass gap between the largest possible neutron stars and the smallest possible black holes. Their merger created a final black hole of 142 solar masses, another object that defies simple classification. What cosmic process forges such strange, intermediate mass remnants? The mystery deepens with the absence of any flash of light, any electromagnetic counterpart to these gravitational rumbles. When neutron stars collide, they often paint the sky with brilliant kilonova explosions, forging heavy elements like gold and platinum. But these unexplained signals come alone, from sources that are either completely dark or so shrouded that their light cannot escape. This points to exotic objects, perhaps primordial black holes formed in the dense first moments of the Big Bang, or other entities made of dense, exotic matter that our current physics cannot describe. Could the faint, persistent hum of the gravitational wave background, a statistical murmur picked up by combining many observations, be hiding the collective voices of countless such exotic events? Each unidentified chirp on our detectors is a direct challenge to Einstein's theory of general relativity, testing its limits in the most extreme gravitational regimes imaginable. What are these dark, massive objects that warp spacetime without a whisper of light, and what do they tell us about the true population of hidden giants lurking in the cosmic dark? This search for the faintest ripples in reality leads us to examine the oldest light there is, a fossil glow that holds its own set of profound and unsettling anomalies. Embedded within the faint glow of the universe's first light is a cold stain on the sky, a region so improbably frigid it defies the smooth story of cosmic birth. This is the cosmic microwave background cold spot, an immense and chilling anomaly in the ancient radiation left over from the Big Bang. When the Planck satellite mapped this primordial afterglow in exquisite detail, it confirmed that this particular patch of space is significantly colder than our best models of cosmic inflation can explain. The temperature difference is tiny in absolute terms, just a few millionths of a degree, but its scale and statistical significance are colossal. Cosmologist Laura Mersini-Houghton has been a leading voice in studying this enigma, proposing that it could be the imprint of a collision with another universe in the vast multiverse, or the signature of a cosmic texture, a flaw in the fabric of spacetime from the universe's violent beginnings. The core of the mystery is probability. Standard cosmology allows for some random cold and hot spots in the background radiation, but the size and depth of this cold spot make it a statistical outlier of monumental proportions. It is simply too big and too cold to have likely formed by chance alone in a uniformly expanding cosmos. One proposed explanation involves the integrated Sachs-Wolf effect, where light loses energy as it climbs out of a gravitational well. If this cold spot overlapped with a supervoid, an immense region of space with very few galaxies, the light passing through it would indeed cool slightly. Yet, when astronomers went looking, the discovered supervoid in the Eridanus constellation, while vast, is not nearly large enough or empty enough to account for the profound temperature drop we observe. The void and the cold spot seem to be aligned, but the void cannot explain the chill. This leaves us with a profound puzzle written into the oldest fossil we have. Is this cold stain a rare statistical fluke, a cosmic unicorn that forces us to re-examine our understanding of random fluctuations? Or is it something far more extraordinary, a bruise left from a primordial collision with another reality, a tangible hint that our universe is just one bubble in an infinite, frothing multiverse? The very fact that we can pose such a question shows how deeply this anomaly challenges our foundational concepts of reality. This investigation into the universe's oldest light and its unexpected cold spots inevitably draws our focus to the force that now dominates the cosmos, an influence so powerful it is tearing the very fabric of space apart. Two of the most trusted cosmic measuring sticks now point to two different realities for our expanding universe. This is the Hubble Tension, a fundamental disagreement over how fast the cosmos is growing. On one side, we have the cosmic distance ladder, a meticulous method that uses pulsating stars called Cepheid variables and cataclysmic supernova to measure the expansion rate in our local cosmic neighborhood. The work of astronomers like Adam Rees and Wendy Friedman has refined this approach to an incredible degree of precision. Their measurements give us a specific, robust number for the Hubble constant. Yet, when we look at the ancient light of the cosmic microwave background, the Planck satellite's map of the infant universe tells a different story. It infers the expansion rate by studying the subtle ripples in that primordial glow, a snapshot of the cosmos from nearly 14 billion years ago. The number it provides is consistently and undeniably lower. These are not small, marginal errors. The discrepancy is significant, standing at a level of several sigma, which in scientific terms means it is extremely unlikely to be a simple statistical fluke. It is a crisis in cosmology that points to a potential crack in our foundational model of the universe, the lambda CDM model. How can two such precise, independent methods fail to agree? Perhaps unknown systematic errors are subtly influencing our measurements of the Cepheid stars or the supernova. But as teams check and recheck their data, that possibility seems less and less likely. The more thrilling prospect is that we are seeing the influence of new physics. Could dark energy, the force driving cosmic acceleration, be evolving over time, changing in strength since the universe's early days? Or are there additional types of particles like sterile neutrinos that barely interact with normal matter, subtly altering the expansion history? This tension is not just a number on a page. It is a direct challenge to our understanding of cosmic evolution, from its first moments to its ultimate fate. If the local measurement is correct, the universe is expanding faster than we thought, implying a future that unfolds more quickly. Resolving this conflict means we may be on the verge of rewriting the story of everything. This fundamental disagreement about the cosmos's expansion finds a strange parallel in the behavior of its most enigmatic objects, where the rules of physics seem to break down completely. At the very edge of a black hole, a fundamental law of the universe seems to shatter. Quantum mechanics insists that information, the unique identity of every particle that falls in, can never be truly destroyed. It might be scrambled beyond recognition, but it must, in principle, be recoverable. Yet Stephen Hawking's brilliant work showed that black holes slowly evaporate by emitting a faint glow of radiation, eventually vanishing entirely. This Hawking radiation appears to be completely random, carrying no information about what was consumed. If the black hole disappears, what happens to the information that defined all the stars, planets, and particles that ever crossed its event horizon? Is it erased from existence, a cosmic deletion that violates the core principle of quantum physics? This is the information paradox, a profound conflict between the two pillars of modern physics, general relativity and quantum theory. The debate between Hawking and physicists like Leonard Susskind was not just academic, it was a battle for the soul of physical law. One radical proposal to resolve the paradox is the firewall idea. It suggests that the event horizon is not a peaceful boundary but a searing wall of energy that instantly incinerates anything that contacts it. This would preserve information by preventing anything from actually entering the black hole in the first place, but it creates its own violent contradiction with Einstein's theory, which predicts an observer should cross the horizon without noticing anything unusual. An even more mind-bending solution is the holographic principle. It posits that all the information describing the three-dimensional volume inside a black hole is actually encoded on its two-dimensional surface, the event horizon, like a cosmic hologram. The three-dimensional world we experience inside could be a projection from information painted on the boundary. This idea finds a mathematical home in the AD/S/CFT correspondence, a theoretical framework that shows how a gravitational universe can be perfectly described by a quantum field theory on its lower dimensional boundary. It is a compelling duality, suggesting information is never lost, only translated. But this remains a theoretical elegance without any experimental proof. How can an object that warps spacetime into a singularity simultaneously respect the delicate, no-deletion rule of quantum information? The answer to this question may not lie in the void of black holes themselves, but in the strange states of matter that could exist within them, substances so exotic they rewrite the rules of physics from the inside out. Within the heart of the world's most powerful particle collider, we recreate a state of matter that has not existed since the first microsecond of the Big Bang. This is the Quark-Gluon plasma, a primordial soup where the fundamental building blocks of protons and neutrons break free from their bonds, allowing quarks and gluons to roam without confinement. We expect this superheated fluid to behave in certain ways, governed by the equations of hydrodynamics that describe how any liquid should flow under immense pressure. Yet the data from detectors like ALICE at the Large Hadron Collider tell a different story. When lead nuclei are smashed together at nearly the speed of light, the resulting fireball expands not as a uniform sphere, but with a distinct anisotropy. It flows more easily in some directions than others, as if shaped by an invisible, complex pressure that our models do not fully capture. This anisotropic flow is a fingerprint of the strongest force in nature, the strong nuclear force, acting in conditions of extreme energy density. Physicists like Urs Wiedemann analyze these patterns to decode the fundamental properties of this perfect liquid, which has an astonishingly low viscosity, flowing with less resistance than any substance we know. The surprises continue with a phenomenon called jet quenching. In these collisions, high-energy quarks or gluons should punch through the plasma and emerge as a spray of particles, a jet detected on the other side. But often, one of these jets is completely quenched, its energy absorbed and dissipated by the dense plasma. It is like firing a bullet into a pool of water and watching it vanish without a splash. This tells us the quark-gluon plasma is incredibly opaque and interactive, a medium that scrambles the signals of its own constituents in ways we are still striving to understand. Even stranger is the ridge. This is a long-range correlation observed between particles emerging from the collision, a mysterious coordination in their angles that persists even when the particles are far apart. It was a shock to find this ridge not only in heavy ion collisions, but also in the seemingly simpler smashing of protons. This suggests that even these smaller collisions may be creating tiny, unexpected droplets of this primordial state. Then there is the mystery of strangeness enhancement. The plasma seems to have a peculiar preference for producing strange quarks, a heavier flavor of quark, in greater abundance than our statistical models predict. It is as if the hot soup readily cooks up these more exotic ingredients, challenging our understanding of how matter forms from the cooling plasma. Each of these anomalies is a clue. They are telling us that our maps of the strong force which binds the atomic nucleus are incomplete under these extreme conditions. What new phase of matter, or what unknown interaction between quarks and gluons, are we glimpsing in these fleeting trillion-degree fireballs? The search for answers in this primordial soup leads us to consider another pervasive cosmic mystery: the origin of the magnetic fields that thread the void between galaxies. A ghostly magnetic force field woven through the emptiness between galaxies guides the universe's greatest journeys. These cosmic magnetic fields are not the simple dipoles of a bar magnet. They are vast, structured, and immensely powerful, stretching for millions of light years. We detect their presence indirectly through two key signatures. The first is synchrotron radiation, a distinctive glow emitted when high-energy electrons spiral along the field lines at near light speed. The second is Faraday rotation, where the magnetic fields subtly twist the polarization of radio waves as they travel through space, revealing the field's strength and direction. The sheer scale of these fields is what defies explanation. How can a magnetic field remain coherent and organized across distances so vast that light takes millions of years to cross them? Our best models rely on turbulent dynamos, the idea that the churning motion of ionized gas in galaxies could amplify weak seed fields into the powerful ones we see. But these dynamos struggle to account for the field's large-scale order and surprising strength, especially in the pristine voids between galaxy clusters. Cosmologists like Ruth Jura are at the forefront of this puzzle, investigating whether these fields are primordial, imprinted in the universe's first moments during a phase of rapid inflation, or whether they were generated later by the first stars and galaxies. If they are primordial, they would be a fossil from an epoch of physics we have never directly observed, requiring new forces or particles in the early cosmos. If they were generated later, we must find an unknown plasma process capable of creating and organizing magnetism on an intergalactic scale. These fields are far from passive decorations. They play a crucial role in shaping cosmic evolution. They influence how galaxies form by providing pressure that supports gas clouds against gravitational collapse. They are essential for the propagation of ultra-high-energy cosmic rays, acting as a labyrinth that bends the paths of these charged particles and obscures their origins. A stunning example is found in the Virgo cluster, where the magnetic fields are not tangled and chaotic as simple turbulence would predict. Instead, they show a remarkable alignment with the large-scale filamentary structures of the cosmic web, as if the invisible skeleton of the universe is magnetized. This suggests a deep, fundamental connection between dark matter's gravitational scaffolding and the magnetic fields that permeate it. How did these immense, structured fields arise from the formless fire of the Big Bang, and what invisible hand maintains their coherence across the eons? The presence of this pervasive cosmic magnetism hints at a deeper layer of organization in the cosmos, an order that may be intimately linked to the most mysterious force of all, the energy of empty space itself. The very force accelerating the expansion of the universe might itself be changing. Dark energy, the mysterious influence driving galaxies apart, is not behaving as simply as our most elegant equations predicted. Its nature is encapsulated in a single parameter, W, known as the equation of state. In Einstein's model, this is a cosmological constant, a fixed energy density of empty space where W equals exactly -1. But observations are whispering a different story. Data from distant supernova and the subtle imprints of Baryon acoustic oscillations, which act as a cosmic ruler, suggest this value might not be a perfect -1. The measurements hint that W could be slightly different, a tiny but profound deviation implying that dark energy is not a static feature of the vacuum but something dynamic, a field that evolves over cosmic time. Nobel laureate Saul Perlmutter, whose work first revealed the accelerating universe, now explores models like quintessence, a theoretical dynamic energy field that could slowly change in strength. This is not just a minor tweak to the numbers, it is a potential revolution in our understanding of cosmic fate. The anomaly deepens with a growing tension. Measurements of dark energy in our local, modern universe at low redshift seem to tell a slightly different story than the inferences drawn from the ancient cosmic microwave background, a high redshift snapshot. They do not quite agree on how this force has behaved across 14 billion years. The immense dark energy survey has provided a trove of data that consistently points toward the need for a revision to our standard cosmological model. If dark energy is truly dynamic, why does it appear so eerily uniform across the vast expanse of space, and could its gentle push one day turn into a violent rip? The search for answers in this pervasive energy leads us to look more closely at the structures it is pushing apart, to the galaxies themselves and their own mysterious patterns of distribution. Stretching across 10 billion light-years of space, a wall of galaxies exists on a scale that should be impossible. This is the Hercules Corona Borealis Great Wall, a cosmic structure so immense it challenges one of our most foundational ideas about the universe, the cosmological principle. This principle states that on the largest scales, the cosmos should look roughly the same in every direction, a homogeneous and isotropic soup of matter. But when astronomers like Roger Clowes map the positions of gamma-ray bursts, which act as brilliant beacons for distant galaxies, they found this vast concentration, a network of galactic superclusters that defies the theoretical size limit for any single structure. How could gravity have pulled together so much matter into one region in the relatively short time since the Big Bang? The standard model of cosmology, lambda CDM, allows for large structures, but the scale of this Great Wall and others like the Sloan Great Wall pushes against the upper limits of what the model can comfortably explain. These are not just random clusters, they are organized filaments and sheets of galaxies that form a pattern stretching across a significant fraction of the observable universe. Another stunning example is the huge Large Quasar Group, a collection of 73 quasars so vast that light would need over 4 billion years to travel from one end to the other. The statistical probability of such a colossal grouping forming by chance in our current model of the universe is exceptionally low. It forces us to ask whether the initial seeds of the universe, the quantum fluctuations from inflation, were not as smooth and random as we have long assumed. Perhaps the early cosmos was imprinted with primordial giantness, a predisposition for matter to clump on scales we are only now beginning to comprehend. The existence of these structures suggests that either our universe is far more textured and lumpy on the grandest scales than we believed, or that our understanding of gravity and cosmic evolution requires a fundamental revision. What does it mean if the grand stage of the cosmos is not a uniform backdrop, but is instead built with colossal, uneven walls that trace a hidden architecture from the dawn of time? This profound question about the universe's large-scale structure is deeply connected to the very light we use to observe it, light that sometimes brings us messages we cannot fully decipher. The light from ancient galaxies holds a secret it was never supposed to tell. According to our foundational model of an expanding universe, the surface brightness of a distant galaxy should fade in a very specific way as its light is stretched by cosmic expansion, a predictable dimming tied to its redshift. This Tolman surface brightness test, a concept developed by physicist Richard Tolman, offers a direct probe of cosmic geometry. Yet when we apply this test, the observations do not always align with the theory. The light from some of the most distant galaxies does not appear as dim as the expanding universe model insists it should be. Researchers like Eric Lerner have pointed to this discrepancy as a potential challenge to the Big Bang paradigm itself, suggesting it could be evidence for alternative models like tired light, where photons gradually lose energy over vast distances through some unknown interaction with the fabric of space. The mainstream scientific response introduces its own layer of complexity, proposing that the galaxies themselves are evolving. Perhaps these ancient stellar cities were intrinsically brighter or more compact in their youth, their stars burning hotter and closer together, which would make them appear anomalously bright to our telescopes. This evolutionary adjustment seems necessary to reconcile the data, but it introduces significant uncertainty into our cosmic calculations. The puzzle deepens when we study specific galactic outliers, such as ultra-diffuse galaxies. These ghostly, spread-out collections of stars exhibit brightness profiles that stubbornly refuse to match our predictions, their faint glow presenting a distribution of light that standard models struggle to explain. If the universe is not expanding as we believe, then what force is responsible for the redshift of distant starlight, and what does that mean for our entire cosmic story? This foundational question about the fabric of space-time leads us to probe even deeper into the realm of the universe's most elusive and ghostly particles. A ghostly ocean of particles from the dawn of time flows through everything you see and touch. This is the cosmic neutrino background, a relic sea born just seconds after the Big Bang, and its subtle influence on the cosmos presents a series of profound puzzles. While the cosmic microwave background gives us a picture of the universe at 380,000 years old, this neutrino background is a snapshot from the first second, a fossil from an even more ancient era. We have never detected it directly, yet we know it must be there, and its inferred properties challenge the very foundations of particle physics. The story of neutrinos is one of constant surprise. John Buchholz's meticulous calculations of the flux of neutrinos coming from our Sun consistently showed a discrepancy with what experiments on Earth were actually detecting. For decades, solar neutrino detectors found only a fraction of the predicted number. The solution was as bizarre as the problem itself: neutrino oscillations. These ghostly particles were not disappearing. They were changing their identities, morphing between three different types or flavors as they traveled. This discovery proved that neutrinos have mass, a fact that is not part of the original standard model of particle physics. How can something so pervasive have a mass so infinitesimally small? The anomaly deepens with the mystery of the neutrino mass hierarchy. We know the three neutrino types have different masses, but we do not know which is the heaviest and which is the lightest. It is like having three boxes of unknown weight. You know they are different, but the order is completely unknown. This hierarchy influences how neutrinos behaved in the early universe and how they shape the largest structures we see today. Their relentless motion in the primordial cosmos, a phenomenon known as free streaming, washed out small-scale fluctuations in the density of matter, effectively smoothing the cosmic web on the smallest scales and leaving a distinct imprint on the clustering of galaxies. This same effect is etched into the cosmic microwave background, altering the pattern of its hot and cold spots in a way that the Planck satellite has been able to measure. Then there is the tantalizing hint of something even stranger, the sterile neutrino. This is a hypothetical particle that would not interact through any force except gravity, making it a ghost of a ghost. Its existence could explain several anomalous results from particle detectors and might even play a role in the formation of the universe's first structures. Could these sterile neutrinos be a component of the dark matter that binds galaxies? The central question remains, why is the universe filled with these nearly massless, shape-shifting particles? And how did their subtle push and pull guide the evolution of everything from galaxy clusters to the cosmic microwave background itself? This exploration of the universe's most elusive particles draws our attention to the empty space they travel through, a vacuum that is not empty at all, but seething with a fleeting, energetic existence. The vacuum of space is not empty, but a seething quantum sea whose energy should have torn the universe apart at its birth. This is the staggering problem of the vacuum catastrophe, a mathematical discrepancy so vast it is almost incomprehensible. Our two most successful theories, quantum field theory and general relativity, clash violently here. Quantum theory tells us that empty space is alive with virtual particles constantly flickering in and out of existence, and it calculates the energy density of this quantum foam. The result is a number for the cosmological constant, the energy of empty space, that is 1 followed by 120 zeros too large. If this were true, the repulsive force of this vacuum energy would have blown galaxies, stars, and even atoms apart before they could ever form. Yet when we measure the actual expansion of the universe, we find the cosmological constant is incredibly small, nearly zero. It is as if we calculated the water pressure at the bottom of the ocean, but when we looked, we found only a damp sidewalk. This is not a small error. It is the largest mismatch between theory and observation in all of science. Physicists like Steven Weinberg grappled with this, even exploring the anthropic principle, the idea that we can only observe a universe where this value is small enough to allow for our existence. Other theories, like supersymmetry, proposed a cancellation mechanism where partner particles would perfectly negate the vacuum energy, but we have found no evidence for such perfect symmetry in nature. We can even demonstrate this vacuum energy in the lab through the Casimir effect, where two metal plates placed incredibly close together in a vacuum are gently pushed together by the quantum fluctuations outside them. But this measured force is infinitesimally small, a tiny whisper of the theoretical roar. How can the vacuum be so full of potential energy and yet exert such a gentle cosmic push? The vacuum catastrophe is not just a number, it is a direct challenge to our understanding of nothingness itself. It forces us to ask if we are fundamentally wrong about the nature of empty space, or if some profound new physics is waiting to be discovered that will reconcile this cosmic contradiction. This fundamental puzzle about the energy of nothing finds a haunting parallel in the story of a substance that should be everywhere, but has almost entirely vanished from the cosmos. A rain of antimatter falls from space, but in all the wrong proportions. High above our planet, experiments like Pamela and the Alpha Magnetic Spectrometer, led by Nobel laureate Samuel Ting, have been meticulously counting the cosmic rays that strike our atmosphere. They detect antiprotons and positrons, the antimatter counterparts to protons and electrons, yet the numbers tell a confounding story. The positron fraction, the ratio of positrons to all electrons, does not decrease with energy as our models predict. Instead, it rises steadily, creating a clear and puzzling excess. One natural explanation points to pulsars, the rapidly spinning corpses of massive stars, whose powerful magnetic fields and winds could be generating these particles. Yet, when we model the combined output of all known pulsars, the math often fails to fully account for the observed surge. This discrepancy has fueled the tantalizing hypothesis that we are seeing the indirect signature of dark matter. If dark matter particles are their own antimatter counterparts, they could annihilate each other when they collide, producing a spray of standard particles that includes this excess of positrons. The data from AMS-02 is precise enough to show a subtle peak in the positron spectrum, a possible fingerprint of a specific dark matter particle mass, but a conclusive match remains elusive. The mystery deepens when we look for heavier antimatter. We have detected no antihelium nuclei. This absence is profoundly significant. The production of an antihelium nucleus in space would require an environment as energetic as the early universe, a place where primordial antimatter might have survived. Finding just one would suggest the existence of entire antimatter regions in the cosmos, a concept for which we have no other evidence. The fact that we see none places a powerful constraint on cosmological models, effectively ruling out large domains of antistars or antigalaxies. Why does this specific antimatter signature appear where we do not expect it, while the heavier forms we might predict are entirely absent? The search for answers in these particle ratios leads us to look at the smallest and most dark matter-dominated galaxies we know. These faint, orbiting specks of starlight hold secrets that could unravel our understanding of dark matter. Dwarf galaxies, the smallest and most ancient galactic systems, are not behaving as our most sophisticated simulations insist they should. This is the core of the missing satellites problem. When physicists model the formation of a large galaxy like our Milky Way within its vast dark matter halo, the simulation predicts that thousands of small dark matter clumps should surround it, each massive enough to host a visible dwarf galaxy. Yet when we look at our local cosmic neighborhood, we see only a few dozen. Where are all the missing dwarfs? This stark mismatch between prediction and observation forces us to question the very properties of dark matter itself. Could it be that dark matter is warmer than we think, its particles moving too fast to coalesce into the smallest clumps, thereby preventing numerous tiny galaxies from ever forming? Or have most of these potential dwarfs simply failed to light up with stars, remaining as invisible dark matter ghosts drifting unseen through the void? Astronomers like Beth Willman meticulously map these faint systems, using their motions to weigh the dark matter that holds them together. The puzzles only deepen with the too big to fail problem. This curious name refers to the most massive dwarf galaxies we do observe. According to the simulations, the largest dark matter subhalos around the Milky Way should be so dense and gravitationally powerful that they could not possibly fail to form bright, massive galaxies. Yet the actual dwarfs we see, like the Draco and Ursa Minor systems, are far dimmer and less dense than these predicted giants. Their stars move with a velocity dispersion, a spread of speeds, that indicates a much gentler gravitational grip than the models allow. It is as if the most formidable cosmic neighborhoods are occupied by only the faintest of tenants. What prevents these seemingly prime real estate halos from blazing with starlight? One leading idea involves dramatic feedback from supernova. In the early universe, the first massive stars in these small dwarfs would have lived short, violent lives and exploded. These powerful blasts could have heated and expelled vast amounts of gas, starving the galaxy of the fuel needed to form new stars and effectively stunting its growth. Another, more radical possibility is that dark matter is not entirely cold and collisionless. What if dark matter particles can interact with themselves through some unknown force, creating a gentle friction that smooths out the dense central cusps predicted by simulations into the softer cores we actually observe? The cores of dwarf galaxies like Fornax appear less cuspy, their dark matter more evenly distributed, which aligns with this idea of self-interacting dark matter. How do these tiny, fragile galaxies retain their ancient structures for billions of years against the tidal forces of their giant galactic hosts? Their very existence and their puzzling properties are a direct probe into the nature of the universe's most dominant, yet most elusive substance. As we scale down from these galactic mysteries, we find that even our own celestial backyard holds its own set of peculiar inconsistencies. Two spacecraft, billions of miles from home, were slowing down for a reason no one could explain. This was the Pioneer Anomaly, a subtle but persistent drift observed in the trajectories of the Pioneer 10 and 11 probes as they journeyed into the void beyond Saturn. For decades, meticulous analysis of their radio signals revealed a tiny, sunward deceleration, a constant tug backward so slight it was like an invisible hand gently applying the brakes. The physicist John Anderson and his team spent years chasing this ghost in the data, a signal so faint it was buried in the noise of engineering models and thermal effects. The leading explanation pointed to the spacecraft themselves. Their radioactive power sources generated heat, and this heat, radiating off the complex surfaces of the probes, could create a tiny thrust. The key was anisotropy, meaning the heat did not radiate evenly in all directions. A little more power pushing from one side than the other would be enough to produce the observed slowdown. This thermal answer seemed to solve the puzzle, but like all good mysteries, it left behind a residue of doubt. Precise reconstructions of the heat flow could not entirely eliminate the anomaly, leaving a whisper of a signal that some researchers argued could be new physics. This tiny discrepancy lives on in the data, a question mark for future deep space missions like New Horizons, which travels a different path and may yet feel the same subtle pull. Could this faint deceleration be a hint of modified gravity, a crack in Einstein's theory revealing itself only in the weak, sprawling gravitational fields of the outer solar system? The effort to understand the forces acting on these distant probes required us to look not just at the spacecraft, but at the faint light that fills the space through which they travel, the glow of the cosmic infrared background. A faint, all-pervasive glow fills the cosmos, a remnant light from the universe's first fires. This cosmic infrared background is the collective warmth of the earliest stars and galaxies, a fossil radiation that saturates the void. Yet its subtle flickering holds a profound irregularity. When telescopes like Spitzer and Akari mapped this ancient glow, they discovered fluctuations in its brightness, tiny patches of excess light that are far too pronounced to explain. The pattern of these variations, known as the angular power spectrum, creates a map of the early universe that does not match our simulations of galaxy formation. It is as if we are hearing a cosmic chorus from the dawn of time, but the voices are far louder and more numerous than our sheet music predicts. Cosmologist Alexander Kashlinsky and his team have meticulously analyzed this infrared excess, finding a signal that persists even after subtracting the light from every known galaxy. What unknown populations of objects are contributing to this pervasive background hum? One thrilling possibility points to the very first stars, monstrously large and brilliant suns that formed from pristine hydrogen and helium. These population 3 stars would have lived fast and died young, flooding the cosmos with intense infrared radiation as their light was stretched by the expanding universe. Their collective output could account for the anomalous glow, offering a direct window into the epoch of reionization, when these first stars burned away the cosmic fog. An even more exotic candidate involves primordial black holes. These hypothetical objects, which could have formed from dense fluctuations in the universe's first second, might have been abundant in the early cosmos. As they evaporated or accreted matter, they would have released energy, potentially contributing to this unexplained infrared signature. Some theories even suggest that the decay or annihilation of certain types of dark matter particles could produce the observed fluctuations. Why does the pattern of this ancient light refuse to align with our models of cosmic structure? This infrared whisper from the infancy of everything suggests that the universe's first chapters were written with a richness and complexity we are only beginning to sense. Just as the foundational light of the cosmos reveals unexpected structures, so too does the bedrock of physics itself seem to shift, challenging the constancy of the laws that govern reality. The very laws of physics may not be the same in every corner of the cosmos. This is the staggering possibility raised by the final and perhaps most profound anomaly, the apparent variation of the fine structure constant. Known as alpha, this number is a fundamental physical constant that governs the strength of the electromagnetic force. It dictates how light and matter interact, how atoms hold together, and even the very chemistry of life itself. For decades, we have assumed that alpha, like the speed of light, was a fixed and immutable pillar of reality, a true constant across all of space and time. Yet observations of distant quasars suggest this may not be so. The light from these brilliant beacons travels for billions of years to reach us, and on its journey, it passes through ancient clouds of gas. These clouds absorb specific wavelengths of light, creating a unique barcode in the quasar spectrum. A team led by astronomer John Webb analyzed these absorption lines and found something deeply unsettling. The patterns suggested that the value of alpha in those distant gas clouds was subtly different from its value here on Earth. The implication is that the electromagnetic force was slightly weaker or stronger in the distant past, or in a different direction in space. The statistical significance of this finding has been debated, with questions about potential systematic errors in the instruments or in the models of the interstellar medium. Yet the signal persists, a ghost in the data that refuses to vanish. If this variation is real, it shatters a foundational principle of physics, the Einstein equivalence principle, which assumes the constancy of the laws of nature. This could point toward theories like string theory, where extra dimensions of space could cause fundamental constants to fluctuate. In such models, a hypothetical field called the dilaton could be slowly evolving, causing alpha to change over cosmic time. To test this locally, scientists use incredibly precise atomic clocks. By comparing clocks based on different elements over months or years, they can hunt for any tiny drift in the fundamental forces. So far, these local experiments have found no variation, placing tight constraints on any change. This creates a tension between the local, present-day universe and the deep cosmic past. Why would the constants of nature be different there and then, but appear rock solid here and now? The fine structure constant is a number woven into the fabric of reality. If it can change, then the cosmos is not built on a fixed foundation, but on a stage that is slowly, imperceptibly shifting. What does it mean for our understanding of the universe if its most basic rules are not written in stone, but are merely a local ordinance? Our journey to map the cosmos stretches back to the first moment a human looked up at the night sky and saw not just points of light, but a puzzle to be solved. Ancient astronomers charted the regular motions of the planets against the fixed stars, creating the geocentric model that placed Earth at the center of all things. This was a reasonable conclusion from their vantage point, but it was ultimately a cosmic illusion. The work of figures like Copernicus, Galileo, and Kepler systematically dismantled that illusion, revealing a sun-centered system governed by mathematical laws. Each of these shifts was born from an anomaly, a stubborn observation that refused to fit the prevailing wisdom. When Edwin Hubble observed that the faint nebulae were actually distant galaxies fleeing from our own, he uncovered the most profound anomaly of his time, the expanding universe, which itself shattered the earlier concept of a static, eternal cosmos. This pattern repeats through history. Vera Rubin's meticulous measurements of galaxy rotation did not just add a new fact, they exposed a fundamental gap in our understanding of gravity and matter, forcing us to invent the concept of dark matter. These pioneers did not have all the answers, but they asked the right questions, using the best tools available to them, from simple telescopes to photographic plates. Our current Lambda CDM model, with its dark energy and cold dark matter, is the latest in a long line of frameworks, a best-fit explanation for the universe as we see it today. Yet the 25 anomalies we are exploring are the modern equivalent of those past discrepancies, the subtle tremors that hint at the next great revision. What patterns can we see in this relentless pursuit of truth? It is a story of tools and imagination evolving together, where each answered question unveils a deeper, more complex layer of mystery. The cosmos does not give up its secrets easily, and our understanding is not a destination but a continuous, unfolding journey. These 25 cosmic riddles are not isolated curiosities, but individual threads in a single, vast tapestry of mystery. When we step back to observe their collective pattern, three powerful themes emerge, revealing the fundamental limits of our current understanding. The first and most striking thread is the sheer prevalence of the invisible. From the dark matter halos that grip galaxies to the missing baryons hiding in the cosmic web, and from the ghostly pull of dark energy to the pervasive sea of neutrinos, we are consistently confronted by a reality where the majority of the universe's substance does not interact with light. Our cosmos appears to be built primarily from components we cannot see, suggesting that our standard model of particle physics is not just incomplete, but may be describing only a tiny fraction of what actually exists. This leads directly to the second theme, the compelling need for new forces and new particles. The strange behavior of Quark-Gluon plasma hints at unknown interactions within the strong nuclear force. The Matter-Antimatter Asymmetry requires a new kind of particle physics to explain why anything survived the Big Bang. Anomalies in the decay of certain particles at facilities like CERN point to potential fifth forces or hidden sectors of reality, a dark sector with its own unique rules and constituents. Finally, these puzzles reveal profound surprises in cosmic evolution itself. The existence of structures as vast as the Hercules Corona Borealis Great Wall challenges the smooth narrative of inflation. The Hubble Tension suggests the expansion rate of the universe is not a simple story. and the flickering of Tabby's star implies stellar life cycles we have not yet classified. How do these threads guide the path forward for science? They tell us that the next great leap will not come from simply refining our existing models, but from a courageous step into the unknown. The collective evidence points toward a unified problem, a cosmos where visible matter is merely the froth on a deep, dark, and dynamically complex ocean. By connecting these 25 dots, a coherent picture emerges of a reality governed by principles we are only beginning to sense, setting the stage for one final, overarching question about our place within this newly revealed cosmos. From dark matter's ghostly grip to the flickering of ancient starlight, these 25 anomalies form a single, undeniable message. Our understanding of matter, from the smallest particles to the largest cosmic structures, is being challenged at every turn. The invisible scaffolding of dark matter, the phantom push of dark energy, and the whispers of primordial antimatter all point toward a cosmos where the familiar substance of stars and planets is merely the visible fraction of a far richer and more mysterious reality. These puzzles are not failures of our science, but its greatest triumphs. They are the signposts pointing toward the next frontier, the unresolved questions that push innovation in our telescopes, our colliders, and our very theories of physics. Each one is an opportunity to refine our models, to shed outdated assumptions, and to explore deeper truths about the fabric of existence. This journey reminds us of a profound humility, that we are part of a universe still actively revealing its secrets. The greatest discoveries lie not in what we already know, but in the mysteries that remain. We encourage you to stay curious, to follow and support the scientific endeavors that tackle these cosmic riddles. Share your thoughts in the comments below. Which of these 25 anomalies captures your imagination the most? If you are eager to continue exploring the cosmos's deepest secrets, subscribe for more journeys to the edge of our understanding. The universe's greatest puzzles are still waiting to be solved.